cooling towers are great air washers. Every little piece of junk, and that's a technical term, junk, that's in the air gets washed out into the tower, and the tower essentially collects debris, all sorts of particulates, etc. As you have a cooling tower operating, it's pulling in the outdoor air. That outdoor air brings with it contaminants. The water washes it out, and it gets into your system. What I'm going to be talking about here, and I think it's probably worth discussing this, is mostly the outside or the open portion of the cooling tower, the cooling system. That's the portion that is directly in contact with the outside air and collects this dust and dirt and debris. The closed loops portion, or typically the chilled water portion of the chillers, usually is not exposed to the contaminant loads that the outside is. There are obviously certain cases where filtration of the closed loop portion is called for. Maybe some people would even say it should always be done. But for the most part, it's a smaller or a less critical issue than the open tower because of the continual addition of particulates to the system. And obviously, there's many different ways that this can affect you. You've got dirt buildup, corrosion, clogging, reduced life of components such as pumps, pump seals, etc. There's a lot of different things that can go on with dirt, so just want to get rid of it. So how much filtration do you need? If you ask a guy who sells filtration, and I'm one of them, generally we're going to tell you that any filtration is good and more filtration is better. So that's a pretty vague description. It's kind of hard to quantify exactly what you need. As Mike discussed, it's very important to take a look at what sort of particulate distributions you might have, what your needs are of your system. But in general, more filtration is a good thing, with one sort of exception. You need to balance the filtration with water use and what your goals are. Because filtration systems require water to operate. Now, I'm going to go through this. In many instances, this does not necessarily increase the amount of water that your system uses, but it can, and it's worth it to explore that a little bit. And of course, you want to make sure that what you're filtering matches what your concerns are. We talked a little bit about bleed. I won't spend too much time talking about that. I'm going to jump right to this drawing, and I was asked to contribute some drawings to this presentation to the manual. This is one I didn't provide. However, I kind of regret that because I think this is probably one of the most important things to look at here, and is probably worth sketching down in general sense. So what we're looking at, and this is very similar to the one that Mike pulled up, but there's one thing that's been added here. This is the amount of water that in this case, a 100-ton cooling tower uses at different cycles of concentration. And as you increase cycles of concentration, obviously your overall water use, which is the top line, decreases. As you increase your cycles of concentration, the additional savings gets less and less and less. And you sort of approach asymptotically this line down here, which is the overall evaporation required to do the 100 tons of cooling we're talking about here. So in a general sense, to kind of step out of the whole issue of water treatment and filtration, this amount of water use right there is what is required by your heat load. So where the big sense is if you can reduce your heat load, obviously you can significantly reduce water use in your system. And so, you know, you could be talking about things like the efficiency of the chillers that we were talking about previously in the question and answer session, or you could be looking at more efficient lighting, lower lighting levels, better glazing, all these sort of things that we don't normally think of as water savings opportunities are basically available in there if you can reduce load. So energy conservation really is water conservation. And in a lot of sense, since it takes water, takes energy to deliver water and to treat water, water conservation is energy conservation. So it's important to kind of look at that in the big picture. What we're talking about and what Mike was pushing for is we want better water treatment. And in general, in the sense of water conservation, better water treatment means higher cycles, means reducing this additional portion of water needed to have a successful water treatment system. And so he discussed a target of 15 cycles, and I'm not going to get into that. That seems actually pretty reasonable for what my experience here. But the idea is we want to push this over that direction. We'll talk about 3 types of filtration you typically see: bag or cartridge type filters, sand filters, and centrifugal separators. Jump right into bag filters. These are pretty simple devices. You've got some sort of canister that has a cartridge of some sort of media in that the water runs through. It's got small pore size, strains out the particulates. It's pretty much what we think of when we think of a filter. These things come in very many different medias for very different target filter sizes. They don't use really any water for blowdown or cleaning. Essentially, the way you regenerate your filtrations, you take the cartridge out and you throw it away and put a new one in. There are some permanent bags that can be used, and these are used mostly in sort of low or very large particle size filtration systems that can be taken out and washed. It should be obvious that water being used to wash it does affect the overall water use of your system, so that should be taken into consideration. There's many different ways to determine how to change these out. I've kind of highlighted, when I discussed my slides I've kind of highlighted what is probably the most water efficient. These can be done manually or schedule, or can be changed out based off of a pressure reading. The thought is, if you're reading a pressure across that, you will know when that filter is loaded up and when it needs to be thrown out, so why do it more often than you need to? So my general recommendation is that sort of system should be monitored with a pressure reading across the filter. Generally, these are used in closed loop systems and not often in open loop, although on occasion you'll see them there. Sand filters, this is the other common type of system used in open systems, and one of the main advantages for this type of a system is it's regenerable, and you have a permanent media in there. A good example of this is you've got, or a good diagram of this is you've got water that comes in through distribution chamber that goes down through this permanent media. The media is selected for a certain pore size, so there's different types of medias that can be in there, and then the water leaves out through the bottom. And that goes through a series of tubes to collect the water and go back to the system. When you wash it, you kind of reverse the cycle. Got a couple diagrams of that, show that a little bit better. In normal operation, loading it, the water goes through the media, comes out clean. The particulates are left in the interstitial area between the grains of whatever the media is. To backwash, the water runs the other way, comes back through the media. It lifts those particles up, or lifts the media up. The particles caught in the media gets taken out, and then that water is taken out to drain somewhere and is taken out of the system. So the particulate matter gets taken out with it. The advantage of this type of a system is, one, as I said, it's regenerable, but also it is probably one of the most efficient regenerable processes. You can get to 5 to 10 microns is typically what you see on those. But they do have heavy water use because you need to backflow for a full 3 minutes. Now, generally, these things are in side stream operation, so put some numbers to that. If it's a 1,000 gallon per minute system, cooling system, which is about 330 tons plus or minus, you would run generally anywhere from 10 to 15% of the water through here. So say it's 1,000, that becomes 100 GPM that you're running through the filter all the time. When you backwash it, that means you are going to be dumping 300 gallons down the drain every single time you operate that thing. So it's just to get an idea of what we're talking about. Usually we'd recommend city water for this because of the fact you're taking so much water out of the system. The problem with that is sometimes you don't have the waste piping size, or if you're doing metering on the discharge of it, that might be a pretty large size meter. So sometimes that people will use the process water, and this type of a system can, more than other types, significantly affect the cycles of concentration. And again, you can schedule this either on a schedule, time clock, or based off of a pressure reading. And again, I would recommend doing it only as often as you need to based off of pressure reading. The last type of filtration I'll talk about is a centrifugal separator. These are a little more complex device. They operate on the process of centripetal force. The water comes in through the top. It circles around at a very high rate of speed, throwing the particulates out. And then in a quiescent bottom chamber, the particulates fall out. And then the clean water runs back up through the center, back to your system. And then periodically, the bottom chamber is cleaned out by opening a valve. The water washes out and back to either the drain or, in some cases, a recovery vessel. These are often used and packaged with a pump. They can also be provided in a side stream or using the pressure drop across the main pump of the system to drive them. The main disadvantage of this type of system is it typically only affects larger particles and only heavier than water particles. And a lot of times you'll see concerns with cottonwood fluff in the system, and so this system is not really effective against that sort of system. It uses very little water compared to a sand filter. There's only a partial flow of water for 30 seconds. It usually ends up being 20 to 30 gallons, plus or minus, depending on the size of the system. And that water could be run back through a bag filter if you really want to maximize your water conservation. So from a water conservation point of view, this might be a preferable way to go, if it does what you want it to do. And again, what we'll see is that this will be manual, tied in time clock, or a lot of times people will tie this discharge into their conductivity sensor, which is normally controlling their bleed system anyway, so this becomes the normal location for bleed, which is kind of nice. You can kind of kill two birds with one stone. One, the regeneration of the filtration system, and two, the maintenance of bleed in the system. And where you often see this is where people are using these precipitation induction devices. I think there's cavitation and pulse power systems that make a large size particulate in the water and kind of tend to drive the particulate sizes larger, but maybe are not quite as applicable to other systems depending on what your particulate size are. And so just one last comment I'm going to make on this is sweeper systems. These can be set up with either sand filters or with the centrifugal separators, or really any type of filtration system. What that is a series of jets that is arranged to blow filtered water across the basin to lift up the particulates, and then take the particulates into the bulk water so they can be taken out by a return line and strained out of the filtration system. This is a real nice enhancement to a filtration system in that it keeps the particulate buildup off of the basin of the tower, which is probably your primary concern for leakages, and it prevents the underdeposit corrosion that can occur in these locations to a large extent. So without much more to say, I think that's probably as quick as I can get through the filtration issues. Are there any questions?